Good morning. We are going to take a look this morning at stoichiometry and the ideal gas law. Now, if you feel like you're good on stoichiometry, you can just go ahead and do the exercises in 13.2c and 13.2d. 13.2d is about limiting reactants, but if you feel like you could use a refresher, then stay with me. If not, just go ahead and do those exercises. All right, here we go. Use the following reaction. This is an example here to answer the next few questions. Well, there's only two questions, but that's okay. So we have 2 HCl. Where are my menus? Where's my quick? Oh, that's okay. Weird. Anyway, use the following reaction. So here's our reaction. There we go. And the above reaction occurs between gasoline, octane, and oxygen. If 4 moles of gasoline are burned, what volume of oxygen is needed if the pressure is 0.953? All right, so we have a straightforward stoichiometry, but we want to find the volume of oxygen. So you know what, in order to need the volume of oxygen, we need the moles of oxygen. We need to note that we are not at STP, so we won't be able to go straight to volume using 22.4. So instead, we're going to use our moles of oxygen. Get there first. So we're starting with 4.00 moles of gasoline, which is C8H18. And we want to find the moles of oxygen. So there are 25 moles of O2 for every 2 moles of C8H18. And we get, I cheated and did this earlier, so let's see what we got. 50. We get 50. Well, that makes sense. It's twice as much. Yes, okay. So we have 50.0 moles. Is that right? Yeah. 25 moles of oxygen. Yeah. 50 moles of O2. All right. Now, to find the volume when we are not at STP, we must use the ideal gas law, the pervert equation, PV equals nRT. Solve for V. V is equal to nRT divided by P. And so we have 50 moles of O2 times 0.08206 liter atmosphere per mole. Remember, per mole can be either over moles or moles to the -1 per mole Kelvin, and Kelvin is also to the -1, or you could write that as liters atmospheres over moles Kelvin. Temperature, we have 35 degrees Celsius. Well, that's not going to cut it. 35 degrees Celsius plus 273.15 Kelvin is equal to, once again, I'm going to cheat, 308.15 Kelvin. 308.15 Kelvin. All ideal gas calculations must be done in Kelvin. So we have 308.15 Kelvin. And then on the bottom we need the pressure, which is 0.953 atmospheres. And then if we look at our unit cancellation, moles cancel with moles to the -1 because that's per mole. Kelvin cancel with Kelvin to the -1. Atmospheres cancel with atmospheres, and we are left with liters. So hooray, that equals, oh no, I don't want that draw. There we go. Equals, and again I'm going to cheat, 1326.69. 1326.69 liters, which is then going to round to, I think We've got 3 sig figs here and 3 sig figs here, so that's going to round to 1330 liters. You guys will let me know in the comments if I've made any boo-boos, or you can email me or whatever. All right, so that was good. The next one, ooh, this one is a trick question, haha, because we have 45 liters of carbon dioxide, 45.0 liters of carbon dioxide, and we want to know how many liters of oxygen. And it would be really tempting, and these are both at 0 degrees Celsius and 5.02 atmospheres. So we could go through a whole big long calculation, finding the moles using the ideal gas law, and then converting to moles of oxygen and blah, blah, blah. But these are both at the same temperature and pressure. Same temperature and pressure. And what do we know about 1 mole of gas at the same temperature and pressure? We know that at the same temperature and pressure, equal moles occupy equal volumes. So the mole ratio, the 2 to 25 to 16 to 18, works whether you're dealing with moles or whether you're dealing with volumes, because equal moles occupy equal volumes. So we can do a straightforward calculation like this. We can say the volume of O2 is equal to 45 liters of CO2, 45.0 liters of CO2 times, and we can use the mole ratio, but in this case it's the volume ratio. We want to cancel liters of CO2 and find liters of O2, and that is let's see, liters of O2 is 25 over 16, and we get, did I solve this one over here? I did not. Oh, well, that's okay. I do have a calculator here with me. 45 times 25 divided by 16 equals 70.3125. 70.3125 liters, which is going to round to 70.3 liters of O2. See how knowing this bit here saved us a whole huge lot of calculations? Pretty awesome, yes? Okay, 13.2D. So now we are doing an example related to 13.2D, and I know you don't have this question, but just watch. Okay, you don't have to copy it down. It's all good. Let's see. What volume of H2 gas will be collected when we have 1.10 grams of magnesium reacting with 300 milliliters of 0.800 molar HCl at 1 atmosphere pressure and 25 degrees Celsius? Well, we have, what was I going to say? Oh yeah, we have to write our reaction before we can do anything with this. So we are reacting magnesium with hydrochloric acid. The state of magnesium is solid because all metals are solid except mercury. We have a molarity for our HCl, so that means it is a solution, which means it is aqueous. This is a single replacement reaction, so magnesium is going to replace the hydrogen, and Mg is 2 plus, Cl is negative, so we end up with MgCl2. That's going to be aqueous because all chlorides are aqueous except for, what is it, silver, lead, and mercury. You don't need to know that, but it's okay. Doesn't matter to this question anyway. And we also end up with H being displaced, so that's going to be H2, which is, of course, a gas. All right, balance this sucker. We need a 2 in front of the HCl, and that takes care of it. Now, we need what volume of H? We have two quantities here. We have reactant A, the magnesium, and we have reactant B, the HCl. And that means when we are given quantities of two reactants, that's going to be a limiting reactant problem. Because our 1.10 grams of magnesium can make a certain amount of hydrogen gas, the 300 mils of 0.8 molar HCl can make a different amount of H2 gas. So what we're going to do is we're going to solve. We're going to say how much of that H2 gas can we make? How many moles of H2 gas can we make from the magnesium? And that's going to be 1.10 grams of magnesium times 1 mole per 24.31 grams of magnesium. That's our molar mass of the magnesium. And this one is nice and easy because there is 1 mole of H2 for every 1 mole of Mg. And we get, oh look, I've calculated this out over here. 0.045248. Come back. 0.045248 moles of H2. Our second part of the problem, we need to say how many moles of H2 could we get from the HCl. So we have 300 milliliters, which is 0.3, and we have 4 zeros, 1, 2, 3, 4 liters, because that's 300 milliliters, of 0.800 molar of, remember of means times, 0.800, remember molar means moles per liter, so that's 0.800 moles per liter, and that's moles of HCl per liter. So that's given us moles of HCl, and now we need to calculate the moles of H2. So there's 1 mole of H2. Let's go back to our reaction, and that's going to be for every 2 moles of HCl. 2 moles of HCl. And we get, again, cheat, 0.12. 0.12 moles of H2. So our magnesium could make a smaller amount. That's our smaller amount of H2. And that's coming from the magnesium, which means that our magnesium is the limiting reactant because it limits the amount of product that can be produced. All right, so far so good. What was the question asking us? We wanted the volume of hydrogen gas. Well, we have the moles of hydrogen gas. We know we're 1 atmosphere and 25 degrees. So we are at 1 atmosphere. That's our pressure. Our temperature is 25 degrees Celsius. And the conversion for that, we need to add 273.15 Kelvin. And I just happen to know that that's 298.15 Kelvin because we do that one a lot. All right, so now we have our N, we have P, we have T, we can solve for V. PV equals nRT. Solve for VV is equal to nRT over P. Our moles of hydrogen, not that one. We want to use the smaller number of moles. That one, 0.045248. 0.045248, because we can't make 0.12 moles of H2 because we don't have enough of the magnesium. We will run out of magnesium. All right, so that's how many moles we could actually make from the H2, or from the Mg, H2. And then R is 0.08206 liter atmosphere per mole Kelvin. And temperature is 298.15 Kelvin over pressure is 1.00 atmospheres. And we get, let's see, cheat, 1.1070, which will round to 3 sig figs. There we go. 1.11 liters of H2. So, if you could, try at least 1 or 2 problems from each of the worksheets, 13.2a and 13.2b. Have fun with that, and I hope you're enjoying your break. I will be recording your next lesson very shortly. Bye!